Hello and welcome to Lecture 4, and in this lecture we're encountering one of the central ideas in the whole course, and that's acceleration. If you look back at the previous lecture, you'll see that the motion we were looking at can be broken up into time periods where the slope of the x versus t graph is constant. Now we've seen that the velocity can be thought of as the slope of the x versus t graph. And so constant velocity means a constant slope, and a constant slope is pretty much synonymous with a straight line. So let's start putting this into an equation form. We've been working on going back and forth between motion diagrams and graphs and descriptions. Now let's go to equations. So you all know the equation of a straight line, y equals mx plus b. I'm sure you've had it hammered into your heads. We're now going to use that to write our equation for how x versus t goes in constant velocity motion. So one thing to realize about the equation of a straight line is it's just saying the thing on our vertical axis, y, is related to the thing on our horizontal axis, x, this way, where m is some constant and b is some constant. So all we have to do is say, well, x is the thing on our vertical axis. So it goes over here, where this y is. And t is the thing on our horizontal axis. And so it's going to go over here. And then we already know that the slope of an x versus t graph is the velocity. And then the only thing left is b. Well, b is the y-intercept, or the, in this case, x-intercept, the vertical axis intercept. And so that is the position when time is 0. So we might as well call it x0 for position at time 0. So we can now read it off from this one. In this graph here, we can see that x equals the slope. If you just look at this slope, we go up 1 for a run of 2. So we have a 0.5 meter per second slope. T is just the thing on our horizontal axis, plus x0 is 1 meter. And there's our equation. Rather badly written, but there's our x versus t. In the case of constant velocity, the slope is the same everywhere. And so the average velocity is the same as the velocity at any instant in time. But if the velocity is changing, now you get a curve. And so the slope is changing. And hopefully you recall that the way you define the slope of a curve at any location is by the slope of a tangent line to it. So now we can still talk about average velocities where we connect 2 points on the graph and join them, and the slope of the line joining them is our average velocity. But our instantaneous velocity is something different. It's the slope of a tangent line to a point. Let's just quickly illustrate this. Here we have an x versus t that's a curve. So this object, whatever it is not moving with constant velocity. And let's compare the average velocity from t equals 1 to t equals 4 with some instantaneous velocities. So we know how to get an average velocity. We take the 2 points that are the end times, and we need a rise over a run. And so the velocity is the slope of this straight line. The slope of that line is the average velocity from t equals 1 to t equals 4. On the other hand, the instantaneous velocity at t equals 1 would be a tangent line. So this line right here, I snug that in there, you see there's the tangent line, and you can look at its slope. And similarly, here is the tangent line at t equals 4 seconds. So now you can just see, without doing any calculations or anything, this slope here at 4 seconds is a lot steeper than this slope here at 1 second. This object is speeding up. Last lecture we practiced going from an x versus t graph to a v versus t graph. And we're going to practice mostly in class going the other way, from v versus t to x versus t. Because you need to be able to interpret velocity versus time graphs, and this helps practice that. But let's start thinking about how you do that. And let's look at this very simple case of a constant velocity. And we ask, how far does this object go between t equals 1 second and t equals 4 seconds? Now, if you take a moment, you can see it's 12 meters. But let's see where that comes from. You know that v is delta x over delta t, and this is a constant velocity, so we don't have to worry about v instantaneous versus v average. We can solve that for the displacement, v av delta t. Think about what that means on the graph. V av is this vertical height on the graph, 4 meters per second. Delta t is this horizontal time interval on the graph, the 3 seconds. And so you can interpret this v av delta t as the area of this rectangle right here. Well, that's very useful because it turns out that that always works. Even when the velocity isn't constant, the area under the v versus t graph is always the displacement. And to really show that, you need calculus, so we're not going to, but it is something that's useful. So now let's continue with this idea of a velocity that's changing. We call the rate of change of the velocity the acceleration. You can think of it just the same way as you do any other rate of change, right? It's going to be the change in velocity over the time interval that takes place in. And this is an average velocity. But we're only going to consider constant accelerations. And so the acceleration at every time is always going to be equal to the average acceleration, since we're always going to look at cases where the acceleration isn't changing. And once again, just like any other rate of change, you can think of this as a slope. In this case, it's the slope of the v versus t graph. And notice it'll have a direction. Just like a velocity has a direction, the acceleration will have a direction. For now, we'll see that we can determine the direction of the acceleration from the sine of the slope of the v versus t graph. Now, that'll look sort of bothersome as a way of getting it, and we'll see a better way of determining the direction later on when we look at vectors. So like I already said, once we get vectors, we'll have an easier way to do what I'm about to show you. And I just want to say before I go on that acceleration is really, go have a coffee. When you come back, I may have finished saying really important idea. And there's unfortunately a bit of a barrier that some students encounter with understanding it. And part of the barrier is that we have an everyday definition. In the everyday definition, when someone says accelerating, they mean speeding up. Now, there's nothing wrong with that definition, but it's not useful to physicists. For a physicist, the definition of acceleration is the rate of change of velocity. So anytime the velocity is changing, then a thing is accelerating. So notice, it's accelerating if it's speeding up, just like in the normal definition. But it's also accelerating if it's slowing down. The velocity is changing. And even less intuitively, if the object's motion is changing direction, then the velocity is changing. The velocity is pointing in new directions, and that's accelerating too. Here's an x versus t graph, and you can see it's curvy, so the velocity is changing. So I'm going to draw a motion diagram for this. We're not working precisely with numbers. You should try and draw one too. Yours won't be exactly like mine, but just try and get the main features. All right, there's my motion diagram, and it doesn't matter if yours doesn't look exactly the same as long as you've captured the main features. And the main features that you should have captured are that it is going to the right, which we've defined as positive, and slowing down first. You can see the slope decreasing here. It turns around, the slope is getting steeper, so it's going back to the left and speeding up. And then at some point the slope starts decreasing in size again. It's getting less steep, and so it slows down. So let's go on now, just like we did before, to draw a v versus t graph, and we're going to start by labeling special points. So here's a special point. Oops. It stops right here. And so we know v is going to be 0 at that instant, and we might as well capture that on our graph. Here, it's speeding up, speeding up, speeding up, and somewhere right around here, it starts slowing down. So now we can draw our v versus t graph. Now, we don't actually know how the velocity is decreasing here, but I'm going to say it's decreasing at a constant rate because we're only going to deal with constant acceleration. So there we go. There is v with a constant slope, right? So that's a constant acceleration. And v is starting positive and decreasing, and it hits 0 at this instant. And now, I don't know about you, but it seems like the slope is changing faster here than here, so I'm going to draw this next part with a steeper slope, but it's still a negative slope. Right? You can see that the slope of x versus t is now negative, and it's getting more negative. And now it starts getting less negative, and eventually it hits 0 out about here. Right? There's the time when it hits 0. All right, so let's take that onward and get the acceleration. And we're going to do the same thing because this still works the same way. The acceleration is a slope, right? We know that the acceleration is the slope of v versus t. And so if we just read slopes off, we can see we have a negative slope here, then we have a more negative slope, and then we have a positive slope. And there we go. Now, let's take that back up to the motion diagram and put the acceleration vectors on. So for this first part, up until the point where it slows down, right, or where it stops, right, there's where it stops, the acceleration is negative, which in our sign convention means back to the left. Then, as it is going left but speeding up, the acceleration is still negative. So it's pointing back this way until we get to the next special moment, which is where it stops speeding up. And now the acceleration is positive, like so.